Hello, very good morning to every one of you. So here we comes to the part 10 of the chapter 3 video, where in this video we are going to explain about intermolecular forces, which is van der Waal forces in here. So it is hoped that at the end of the lesson, you'll be able to describe what is van der Waal forces in terms of permanent or temporary dipole and induced dipole, and also deduce the effect of van der Waal forces between the molecular physical properties of the substances involved. Okay. Right, so without further ado, let's begin. So, generally, intermolecular chemical bondings can be divided into two categories of term, which include intramolecular forces and also intermolecular forces. So basically, the differences between intramolecular forces and intermolecular forces is intramolecular forces is actually also known as the bonding forces, where it involves all the three chemical bondings that we discussed so far. So we have already discussed ionic bond, which has the highest bond energy among the three chemical bonds that we discussed, okay? Where then we have covalent bond, which is relatively stronger, and then among the three of them, then metallic bond is considered among not the so strong, but still all of them possess generally high bond energy in here. Therefore, this is what intramolecular forces can be used. Okay, so this is the first type of the forces, which is intramolecular forces. The second type, which is actually our main focus of our video, is what we so call as the intermolecular forces, where intermolecular forces is the forces between the molecules, depending on what type of particles they are interacting between each other. Okay, so we have a few examples of the intermolecular forces. Like here, we have ion dipole forces, which is the forces formed in between the positive, in this case, like let's say positively charged ion and partial negatively charged of a polar molecule. Okay, so ion polar molecule has a relatively high intermolecular forces, which is 40 to 600 kilojoule. And then the second one, which is actually part of our focus, in our part 11 video later, where we are going to discuss hydrogen bonding. So in this part of the video, we are going to focus more on these three dipole forces, which is formed between polar molecules. We have dipole-induced dipole forces, which is formed between a non-polar to a polar molecule. And then we also have induced dipole forces, which is also known as the London forces in here, which is the weakest among all the intermolecular forces that we are going to discuss later. Okay, so these intermolecular forces are generally weaker as they were involving the forces in between the two particles, and therefore there is no direct bond between these particles, right? Okay, so let's have a look at how does the intermolecular forces will influence the physical properties. So before we go into the physical properties, let us understand what is boiling point. So boiling point is defined as the temperature at which the vapor pressure are equal to the external pressure surrounding the liquid, causing the transition from liquid to become gas. Okay, so in a covalently bonded molecule, generally the weak van der Waals forces can influence very much on the intermolecular forces in between the covalently bonded molecule. Okay, so van der Waals forces can be generally divided into two types. One is known as dipole-dipole forces. Another one is induced dipole. So let's have a look at the differences in between these two forces. So we have dipole-dipole forces, sometimes also known as permanent dipole forces. It's a forces that is formed by polar molecule. Now, if you still remember that previously we already learned about polar molecule, so we learned that highly electronegative elements will have the electron density shift to its particles, causing it to have what we so call as a partial negative charge. Whereas the one which is less electronegative will act like as if some part of the electron density are donated to the more electronegative element, therefore bearing a partial positive charge in here. Okay, so the difference of the separation of charge in between the two atoms in here will establish the dipole. Hence, when covalently bonded molecules are interacting from one to another, we can see that this is how between the two particles they are interacted. So they make use of the polarity of the molecule, where the partial negative charge of the molecule interact with partial positive charge of another molecule in an alternately orderly manner, so that they are held by relatively strong intermolecular forces. Whereas another form of the intermolecular forces is also known as the induced dipole, where induced dipole are also known as temporally dipole forces, where it is formed by a nonpolar molecule. Now, because in a nonpolar molecule, as exemplified by the chlorine, since they have equal magnitude in terms of the electronegativity, so the distribution of the electron cloud between the two chlorine atoms are equally distributed. So at this moment, if they were to interact in between another particles without any polarity, so it is very hard for the two molecules to interact from one to another. Therefore, between the two chlorine atoms, they sort of like negotiate, where at first, initially, so I shift some electron density to you, okay? While here I shift the electron density down. Note that this is all temporarily, okay? So until a certain time, then it will act like, then this one have back, then this one. So the shifting of the electron density in here is shifting of the electron density here is like established in between these two non-polar molecules in here. Therefore, between the induced dipole, they are actually very weak intermolecular forces in between them. That is why we said just now, induced dipole, also known as the London forces, has the weakest intermolecular forces among both of them. All right. Okay. So now you have already, but still, regardless, no matter it is a dipole or induced dipole forces, both of them are also known as weak van der Waals forces generally. All right. Okay. So now we are going to have a look at the factors that influence these weak van der Waals forces. Okay. Okay, so these are the description which I already mentioned just now, where the dipole forces are intermolecular forces attraction that occur between a polar molecule. So they are interacting from one partial positive to one partial negative, as like what I've mentioned. And the strength of the dipole depend on the polarity of the molecule involved. So greater the polarity results a stronger interaction. So these forces are generally stronger than London dispersion forces, but weaker than the hydrogen bond. So dipole forces interactions influence many physical properties, especially boiling point, melting point, and some part of solubility also will be influenced by it. Okay, and then we also just now described about induced dipole. Induced dipole, it is a type of the intermolecular forces that holds in between the non-polar molecules or atoms. So these forces arise due to the temporary fluctuation of electron density within the molecule, leading to a temporary dipole. So even in a non-polar molecule, electrons are constantly in motion, and results the electron density around the molecule may become uneven, creating what we so-called as a temporary dipoles, with slightly positive charge on the one side and slightly negative charge on the other side, as I already mentioned just now. And the strength of the forces increase with the size and the mass of the molecule, as we said that larger molecular mass or molecular size has more electron and a greater total surface area, leading to a stronger temporary dipole, induced dipole in here. Okay, so later we will discuss as one of the major factors that influence this strength of the weak intermolecular forces. So now let's have a look at the factors influencing the weak van der Waals forces. We start from the first one, which is the relative molecular mass, or the molecular size of a covalently bonded molecule. In general, it says that greater the relative molecular mass, okay, or greater the molecular size, greater the strength of the weak intermolecular forces, higher the boiling point of the liquid involved. So that is why when going down to the homologous series, as you can see in here, from methane, ethane, propane, butane, pentane, hectane, hexane. All right. So as the molecular mass increases, relative molecular mass increase, the strength of the weak van der Waals forces also increase, therefore increase the boiling point of these covalently bonded molecules in here. Okay, right. So this is the primary factors that influence the strength of the weak van der Waals forces in here. Okay, so let's together have a look at some specific examples that I prepared for you. Where in here, let's say we are talking about the carbon halide. Okay. All right. So let's start from this one first. Okay. Okay. As we already learned in the polarity of the molecule, where the electronegativity of the fluorine is the highest, followed by chlorine, bromine, and also iodine in here. Okay, so even though fluorine has the highest electronegativity, while iodine has the lowest electronegativity, when it comes to the intermolecular forces in between tetrachloromethane, tetrafluoromethane, tetrabromomethane, and tetraiodomethane, it seems that the electronegativity does not plays its roles much because the molecular mass differs significantly, where the molecular mass of the CF4 is 88, CCl4 is 154, CBl4 is 336, and CI4 is 520. So as the relative molecular mass increase, okay, the strength of the weak intermolecular forces or the strength of weak van der Waals forces also increase, therefore increase the boiling point of the compound. So in this case, even though you have high electronegativity, but due to the large molecular size, the induced dipole forces formed between a larger molecular size is greater, therefore has a stronger intermolecular forces. Okay, so this factor will not change with the polarity in here. Okay, so as you can see, the molecular mass still plays a major factor, even though in here the polarity seems to increase from CHCl3, CH2Cl2 to CH3Cl, but still, if you look carefully in here, the intermolecular forces between all these are still relatively weak because the relative molecular mass increased with the CCl4 has the highest intermolecular mass of 154, therefore has the highest boiling point, whereas the molecular mass of chloromethane, CHCl3, has the lowest molecular mass, therefore has the lowest boiling point in here. Okay, and this also applies to the same case where in here, if you were to compare between trifluoromethane and trichloromethane 2, so even though CFCl3, in this case, because if you can see very clearly that the molecular mass differ widely, so even though the dipole moment of the CHF3 is greater than that of the CCl3, but still the molecular mass or molecular size of the CHCl3 is much larger than CHF3. So that is why CHF3 still has the lower boiling point compared to CCl3 in here. So as a conclusion in here, from what you can see, how important it is, the intermolecular forces is affected by the molecular mass or molecular size of the molecules involved, right? Okay, so does it mean, teacher, the polarity of a molecule does not influence the strength of the weak van der Waals forces? No. Somehow, in some way, there are also the second and the third factors, which secondly is influenced by the dipole moment. Now, this one, we are now talking about, they have almost the same molecular mass or almost the same molecular size in here. As you can see, propane 44, dimethyl ether 46, methyl chloride 50.5, ethanol 44, acetonitrile 41. So their molecular mass does not differ. The range inside here is plus minus by 10 relative molecular mass in here. However, because propane has the lowest dipole moment, followed by dimethyl ether, methyl chloride, ethanol, and acetonitrile has the highest boiling point. For information, how does this molecule look like? So as you can see, propane, which is a non-polar molecule, dimethyl ether is slightly polar due to the highly electronegative of the oxygens in here. Same goes with the methyl chloride. The magnitude is pointing towards the chlorine in here. Ethanol also due to the oxygen is more electronegative, so the overall molecule is pointing upwards to the oxygen in here, and acetonitrile being the highest dipole moment due to the C triple bond H in here. Furthermore, the nuclei is between the CN is closer due to the triple bond that give rise to the dipole moment in between the CH3CN in here. So in here, if molecule has almost the same relative molecular mass, it is greatly influenced by the dipole moment. Therefore, greater the dipole moment, stronger the polarity of the molecule involved, greater the strength of the weak van der Waals forces, therefore higher the boiling point. Now, bear in mind that this is only true for those relative molecular mass does not differ much. I would say that it's plus minus 10-ish, right? So this is the first factor. And then the second factor is the factors of this total surface area in here. Okay, so if you have a total surface area, for these are all isomers of C5H12. Okay, so it seems that N-pentane has the highest boiling point among all of them, followed by 2-methylbutane, while 2,2-dimethylpropane has the lowest boiling point. Okay, so this can be explained by stating that straight chain has a greater total surface area compared to a branch chain. So what is a straight chain? So straight chain is a molecule that has no branch on it. Okay, but if you see like this 2-methylbutane, you have a branch over here, which is the methyl branch in the parent chain. And then for dimethylethane, so this is the parent chain. So this is like a branch in here. Okay, so as you can see, if you have more branch, the total surface area is going to be greater. So can you imagine if you have another N-pentane that is interacting with another N-pentane molecule, the surface of the exposure in between the two long straight chain molecule are greater. So that is why they have the greater strength of the intermolecular forces, therefore higher the boiling point. Okay, so greater the number of the branches, smaller the total surface area, therefore weaker in strength of the weak intermolecular forces. That is why it has the lowest boiling point among all of them. Okay, all right. So with that, that is all about van der Waals forces and what are the factors that influence by it. So that is all for the part 10 of the video, and I'll see you in the next video, which is the final part 11, which we are going to talk about hydrogen bonding. Okay, so with that, we finish our video for part 10. Thank you.